dtrace for hardware, which might seem a little bit weird based on the kinds of things everyone else is interested here. So I'll just tell you that I discovered dtrace because I spend in my day job most of my time writing code for DSPs where there is no OS, or for PowerPCs and VxWorks where there is no OS. So
you guys love hearing that.
So you can't, I love you when you're but the problem is that you have no visibility into the system at all. I also write a lot of VHDL, and equally, you don't really have a lot of visibility into what's happening in hardware after it's synthesized. My research advisor at University of Arizona works on reconfigurable computing, and again, one of the problems is basically his research is in what's called warp processors, which basically have a hardware-based profiler that figures out what math is utilizing the processor most, and dynamically uses an FPGA fabric to synthesize that into the FPGA and then run it in the FPGA. Which, if you're trying to do hard real-time anything, it makes it really hard to know what's going on in the system because you don't really know what's running in software and what's running in hardware. So then the beauty of having, say, a dtrace provider for hardware would be that you'd be able to figure out when it's not doing what you think it should be doing, what's actually going on. So I don't have a demo. Sorry about that. Next year, I promise.
No.
Yes. I'm finishing my degree in December, so we'll be done. But right now, we're kind of at the stage where we're sort of trying to figure out what are the sorts of questions we would ask. Like after you get past the point of how do you create a probe point, how do you fire a probe in hardware, and then how do you get the data out? Because you can't just halt the process and go look at what's in RAM. After you get past that, the question becomes what do you want to look at?
Are you past that? I mean, have you figured out how to do that?
We have a prototype, and it's just got no diagrams in it, so it's really boring to look at. But I think we have at least a straw man for how you, for the hardware that you would need to be able to stick probes in, and then there's a bunch of research into how to do embedded scan chains for hardware objects. So you can just go and stop it, query some buffer that's in the hardware, get the data out, and then let it go again. The question we have now, though, is pretty much what would we want to look at?
And so is the mechanism that you've embedded today, is that completely divorced from dtrace, or is it, I mean, you use it when at the lower level mechanism, you're trying to figure out how to...
Right.
Okay.
So the idea is that then instead of having it, there's some little hardware that sits next to the processor that causes an interrupt that's connected in the OS to dtrace and then looks like a regular dtrace provides that's something. I suppose there would be nothing that would stop you from implementing the same thing in the system tab, but
well, maybe not.
What? I don't know. So I guess I can draw on the whiteboard maybe the sample system we have put together. You can tell me if that is reasonable and something that you would care about, or something that you have no interest in whatsoever. That would be good to know. Because of course, being university people, if you're interested in funding any of these sorts of things, okay. So.
Sorry, are you guys going to have a highlight reel of you just moving whiteboards around back and forth?
Yeah, absolutely.
Up and down.
And saying, thank you guys on genitalia. That's like 60% of the comments. Andrew, is Starbridge Systems still alive?
I'm sorry?
Starbridge Systems?
I don't know.
Okay. Answer that question.
Googling now.
Who are those crazy guys?
I'm Googling now, yeah.
So the system that we're looking at right now is we're imagining an embedded processor, in this case the PowerPC 440, that has a 64-bit processor local bus. This is the IBM bus that I'm embarrassed because it's dropped out of my head for the moment. But So what we have is, we have an image compression unit written in VHDL that implements a wavelet compressor and then an entropy coder, and it's supposed to be getting, say, data in from a camera out here. So eventually you're going to be getting a whole bunch of data, say 30 hertz or 50 hertz coming in from the camera that then has to go over this bus. And one of the questions would be, if this was not working right, if you weren't keeping up with the frame rate, or if your margin on the frame rate were getting small, there are at least two things that could be wrong with this. One, you might have made bad assumptions about the inputs to the wavelet, so you don't get any frequency separation, so you have essentially files that don't get compressed, so you're trying to push way too much data over the bus. Or there could be something else sitting out over here that's hogging the whole bus. So one of the questions that we'd like to be able to answer is, or we think that we can answer with dtrace, is if it stops working the way you think it should, can we tell the difference between bus congestion and badly implemented VHDL, or just wrong assumptions in the VHDL? Thank you. So basically, what we've proposed is that we have this extra little bit of hardware over here, which that's dtrace interface unit. I flew in this morning, so I had to cut it to 3 and forgive me. So basically what this will do is I can either do the sampled mode, where in software I write to the interface right here and just ask it to stop, and then can use a scan chain in here to go and read data out. So if I wanted to just see what the energy in the different subbands of the wavelet decomposition is, I could tell that the images just do not have the kind of frequency content that I expect them to have, and that's why this is happening. Or if I went and looked at that and it looks fine, it looks to be what I expect, I at least have an idea that it might be something that's happening on the bus. The same way I could go and look at the parts of the hardware that are down in this area and just look at how long, what's my average or the standard deviation of the time that when I try and start a bus transaction, when I finish a bus transaction. So again, if there's somebody out here that's hogging the bus constantly, that'll give me a little bit more information. And of course, if the bus controller were instrumented, I would be able to go and ask the bus controller what it is that it's doing.
So the DIU, what is running on that? Is that a? It's
just hardware.
So is that an x86? Is that a PC? Is that a?
No, this is all on chip.
So is the model then that you write a device driver that talks to that hardware, and then that device driver is basically instrumented like the SDT, and that's how it presents the results of the software.
Right. So if you had the PowerPC port of Solaris running here, there would be a device driver that basically, so when this guy would interrupt the core, that interrupt handler would run and say, haven't exactly figured out what the mechanism would be, but would kick dtrace and pretend to be a probe, the way that a probe in software works.
So you may want to look at the profile provider
yes.
for an example of that
right.
kind of thing. We should talk about how you want to name these things, because that's one issue. So absent of PowerPC port, absent of PowerPC port of Solaris, so you use BSD. How?
You also use Unix on it.
Or Unix, yeah, there you go.
Well, you could do, the idea is that it's really not, at least at the level that we've detailed this out so far, and I'm working on the VHDL for this right now, it doesn't really matter.
Well, it has to run on PowerPC.
Right. Well, it has to, if you, there's nothing, I think, that in, say, the right-hand side of the diagram, there's nothing that would keep you from instrumenting the encryption hardware on Niagara 2. So it's nothing that would stop you from doing that. So I think that this, like the specification for what this interface looks like and for what this guy does, there's nothing in it that would keep you from moving it somewhere else. It's just that we have silence boards with 405 and 440 cores in them, so that's the one that give us hardware.
Sure. I mean, we should stop.
So yeah. And we're going to submit the call for proposals opens in April for the Semiconductor Research Corporation, so we're going to be submitting this as a grant. So if you're watching this online, please don't submit it for a grant before I do mine.
Date.
Yeah.
Today is.
But the kind of, I guess, and I don't want to take up all of the time, so this is what we're doing. And basically what I'd like to know is if you think it's a good idea, bad idea, what other, like this, since I do a lot of signal processing stuff, this is an interesting example to me, but I don't know what other interesting examples people have. Or if you just test your hardware enough to know it's always going to work, which I mean, it's an option. A lot of aerospace people do that. They just,
well, I mean, so is this kind of interesting then in the case of a network provider, given you're pushing all that off on a chip?
mm-hmm.
And,
yeah.
I mean, you have your network pros just coming from hardware itself. So
I'll do this to the top.
TCP, yeah.
Or I'll give you another example, maybe a storage example, is something like, there's a whole, this is not building, SAS expanders and troubleshooting SAS expanders, that's something like this where you could basically instrument parts of these separate processors that are basically processing storage frames out of storage fabrics. That would be immensely useful because right now, if you're debugging something like that, basically your choices are either to buy a $30,000 to $50,000 basically trace buffer or SAS element, or to simply be able to view the frames as the IOC sees them as opposed to by using dtrace instrument with the device driver. But because you're building these chains of trees and expanders, there's traffic that's happening in between those out there in the world that you can't see. And it strikes me that the hardware model you have plus the combination of dtrace would probably provide something that would be more effective and also a significantly lower cost solution than what people are charging for those complete hardware solutions. So that's a great application of those. I buy one of those.
Andrew, would you envision enumerating all of the probes that are possible in terms of, what would be an example of a probe name?
That actually was one of the biggest problems we have right now is that the way that electronics designers design hardware is so different from the way that software engineers attack software that figuring out a generic set of probes or probe names ends up being really difficult because this only, like, I can tell you what I might call probe names for these two, except that they only really make sense here. And if it's something that you can't stop and sample, or you do want to stop and sample, I'm struggling with that. So
I wouldn't, don't get too hung up on the need to genericize them. I don't think you need to genericize them. I think actually the issue is more on how they're named. And
okay.
An issue that we have within this would be a good dovetail within John's presentation of the CNC provider is you've got these funky semantics and then like, oh, we can't enable two of these simultaneously, or we can't enable more than n simultaneously. And if you can, provided you can enumerate everything, and the profile provider is very goofy because we have this problem like how do you specify the resolution of the profile provider? And the solution I finally came up with is total hunt, which we have dtrace team are extremely good at. Very good at punting those, is if you come up with a profile probe that doesn't exist, it creates a dynamic probe. So if you make up a frequency, it creates a dynamic probe. So there is some precedent for doing that, but if you can statically enumerate all of your probes, and like I said, don't get hung up on genericization of feedback. This is very, I mean, to me, this is extremely interesting because when I think about reconfigurable computing, I mean, there's great promise for reconfigurable computing, but as I imagine all of us in the room, most of us are software guys, and we know that there's many a slip twixt the cock in the lip in software, let alone when you get FPGAs. So to me, I've always looked at reconfigurable computing and thought the observability problem has to be tackled. So I think this is really, really interesting stuff. Any other comments? Great, thank you.